Today we're going to be talking about 8.4, which is going back to radical notation and nth roots. So if you remember radical notation, a radical is just this symbol here. So it's like your square root symbol, but there could be numbers in here, right? That's what they talk about the nth root, right? So if you said something like this, like 5 with the radical symbol, that's the fifth root. N just stands for like what number you're putting there. In this case, this would be the fifth root. So we're going to be going back to this and using that exponent table like we used before and kind of going a little bit further with that kind of notation, the radical stuff and the nth roots. So the question for today, how can you simplify nth roots and various rational exponents? A rational exponent, if you remember, rational just means it's a fraction. So if we have something like 3 over 5, that would be like your fraction as an exponent. So quickly, remember from last chapter, we talked about whenever you have a number that's greater than or equal to 0 in here, this would be called the nth root of x. That's how you would read this. How do you read this out loud? That's the nth root of x. That's also the same thing if you want to write this without the radical symbol as x to the 1 over n. X to the 1 over n power. Remember, this is an exponent here. So we're going to practice kind of going back and forth between these two again, but we're just going to add something to it. So something a little newer here, we have something called the geometric mean. So if you look at the warm-up, it asks about the arithmetic mean. And that's whenever you when you take an average, you're first taught the normal way to do average is you add up all the numbers you have, and then you divide by how many numbers you're adding together. The geometric mean is kind of a similar way of doing that, but it changes up the method. So the geometric mean is when you take a set of numbers, and instead of adding them together, we multiply them together. And then you take the nth root of the number of values in the set. So this root will depend, the nth root, will depend on how many numbers there are. If there's like 15 numbers, you take the 15th root, is what that's saying. So this is just a different way to calculate average. And this is used a little bit more in things like investments and things like that would make more sense when you have a lot of growth. That's, your money is growing and things like that. They usually use this kind of average called the geometric mean. But we're going to do just a simple example. I think it's like something easy to do like on a test. This example says, find the geometric mean for the shoe sizes in John's family. So when it says geometric mean, that means you take all the numbers and you multiply them together. And then we'll take the nth root. So this is based on how many numbers you have. So first, let's just count how many numbers we have. We have 1, 2, 3, 4, 5, 6, 7. So we're going to take the 7th root of all these numbers being multiplied together. So we do 9.5 times 7 times 6.5, 11. You just write these all out, or rather just put them into the calculator. And depending on what kind of average you're doing, whether it's the geometric or the normal arithmetic mean, you might get numbers that are pretty close. But it's better to do this kind of stuff, the geometric mean, depending on what kind of set of data you have. So if you type this into the calculator, you can do the 7th root of all these things, or you could raise all this stuff up to the 1/7 power. It's the same thing. This number inside here is, already multiplied together, is 2,852,850, I think. If you raise it to 1/7 or do the 7th root, you get the same thing, which is 8.35. It rounds up to 3.36. So this would be like your geometric average or your mean. Pretty simple. You just have to remember that you don't add them together. You don't divide. You do multiplication. So this is all multiply. And then you take the root of how many numbers there are. Okay, so for example 2, this is something that we would probably do in the calculator at school. So if you don't have one of those to use, it might be a little difficult to figure these out. One way we did these before, if you remember, we did the table for this one, or you could just use a calculator for it. So one way you could do this is type it into your calculator, or you could use a table, or you remember we did this a little while ago where we separated out. We did 625 to the 1/4 to the 3rd, and then just figured it out from the table from there. So you could do that. And I can kind of do that as well, I guess. So 625 to the 1/4, I think, is the number 5. And if we raise that to the 3rd power, that would give you 125. And the idea is, if you type this into the calculator, you would actually get the exact same number. So you actually get 125. And then if you type this into the calculator, you would get the same number again, 125. So that must mean something. If all of these things equal 125, that means no matter how you write these out, they're actually all the same thing, just written different ways, right? This has a fraction exponent, 3/4. Notice what it looks like in here. That 4 becomes your root. The 3 can go inside with the radical symbol. Or you could pull the 3 outside and put parentheses around everything. These are all the same thing. So they're all the same. Whoop, how'd that happen? All the same. And for good reason. So we have this new property that if, this is very, very important, as long as we have positive integers, so in here, positive, right? Positive. M has to be greater than or equal to 2, and N has to be greater than or equal to 2. Then we can say this. So here's your M and N. So you can change this to, what can we do? So if you look back here, we can change this to saying 3 and then 4 as a fraction. So over here we would say it was x to the, m we can pull out. Sorry, I guess they're going to go to this one here. You can take the 3 and bring it to the outside. Yep. Put parentheses around it. And then you could also write this as m over n. And you don't have to go in this order, of course. You could just go from this one to this one, or you could go backwards to that, or you could use what's in between. It doesn't really matter. These are all the same thing, just written 3 different ways. And lastly, don't forget, this only works if you have positive numbers, which we're going to show as an example in a second. Just looking to see what we have here. Okay. Our example 3, suppose that we have a positive number in for x. Use the root of a power theorem, which is what this is called, root of a power theorem, to write the 6th root of x to the 18th in 2 other equivalent forms. So I'm just going to practice doing this. Go from one to the next to the next. So we'll do 6th root of x to the 18th. That's this form here, right? And of course I got a mess going on up here, so let me erase some of this. Now we're going to go to this form. So one other way to write this is we could take the number 18 and put it at the outside, put this in parentheses. So we have the 6th root of x raised to the 18th, which also equals, rewrite it like this as a fraction exponent, x to the 18 over 6. And we could go even further because we can actually simplify what 18 over 6 is. That is just the same thing as 3 over 1 or 3, x to the 3rd. So these are all the same thing, so long as you have this. This is key. So I'm going to show you an example of why this has to be positive. We're going to do an example where you throw in a negative number, and when we do a positive number, and you'll see that it works sometimes, it doesn't work. In this particular case, we throw a negative number in, so because this is negative, we're not going to get a good answer here. So we're going to show that if we use the original, see this is the original, that it is not the same thing as x cubed, like we said it is, if we use a negative number. So I'm going to put negative 2 in here for x here, negative 2, and negative 2 here, and see what we get. So on this side, we get 6th root of negative 2 to the 18th. And we're going to show that that is not the same thing as putting negative 2 to the 3rd. So again, I know it's kind of tough because you don't have a calculator, but if you did this in the calculator, what would you get? You can check and see, or you could use like Desmos or something. The right-hand side might be a little bit easier because this just means negative 2 times itself 3 times. That would give you the number negative 8. Over here, however, would actually give you a different answer. This would give you the answer of 8. So they are not the same. Not the same. Now watch how this differs when we go over here and use a positive number. Then we will show that they're the same. So if we do the 6th root, now I guess I could have put that in that calculator. Let me see what that is. Negative 2 to the 18th power. I don't particularly like it. It's only 262,144. I guess I could have done that, but oh well. Over here, we raised 2 to the 18th power. We're going to try putting in 2. We're going to show that it does equal the same thing when we plug in 2 here into the 3rd. So 2 to the 18th would give us the same number. We have the 6th root of 262, 144. And then this would give you 8. See the difference on this side, we got negative 8 because you had 3 negatives being multiplied together. And then if you take the 6th root, I'm just going to go ahead and type in the calculator to make sure I got it right. Yep, you get 8. So this is 8 equals 8. So this is just to show that, negatives don't necessarily work in here, but positives will work. So it's a very important thing. When we're doing this, that we cannot have negative numbers in here. Only positive ones would for sure work. Okay, just as a side, so whenever you come across it and you put a negative number in, you'll know, oh wait, that may not necessarily work. Example 4, we're going to simplify the following expressions in exponential form as long as we have a positive number for x. So we're just going to change this, and our goal is to just change it into an exponent. So I'm going to kind of jump the gun and go from this, kind of skip this step, and go from this to this. So I don't need to write it out multiple times. So I'm just going to jump from x to the what power? No root anymore. Now, if you remember, this is the number that always goes in the bottom. That's all you have to remember. So it goes 35 over 7. And then for these ones, we're going to keep going. If you can simplify it further, this would be the same thing as 7 goes into 35. How many times? 5. And that would be your answer. Okay, B, it's written in the other form where it already has in parentheses, but it's no different. This is your denominator. That's your numerator. So this is x to the 6 over 9. And we'll go a little further, right? Divide these both by 3. So this is x to the 2/3. Which, by the way, if you wanted to take this back into that form, this would be the same thing as saying the cube root of x squared, right? See if you can make that connection. It's the same thing as that. But this is our answer because it wants it as an exponent. And the last one here, we have x to the bottom will be 3, so it looks like it's going to be 21 over 3. So 21 divided by 3 is 7. X to the 7th. Now we no longer have a root here like we did over here. So these two here, the first and the third, do not have any more roots. Well, this one does because you have a fraction still. I think we only have 2 more examples and we're done here. Okay, pretty short. We're going to rewrite a bunch of roots using a rational exponent. So if you remember, it doesn't matter how many roots we have. It's not going to be that difficult. If you remember, the number that's in here when you don't see it, when you read this is actually the square root of the square root of the square root of 6. So like there's a little 2 here for all these, just so you're familiar. I'm just going to rewrite each one as a rational exponent. So if we start on the inside and just look at the fact that we have the square root of 6, that can be rewritten as 6 to the 1/2 power. And so what you end up having here is you have 3 of those in a row. So you would have 6 to the 1/2 power with another. Each one of these creates a 1/2 power. 1/2 with another 1/2. So that's what the square root means every time you have it. 1/2 to the 1/2 to the 1/2. So you're kind of like building up this exponent line here. And when you do that, you just multiply the exponents together. So you do 1 times 1 times 1. This will be 6 to the 1 over 2 times 2 times 2. That would be 4 times 2, which is 8. And that's your answer using rational exponents. All right. The next one, we have the square root of the cube root of the 4th root of 150. So again, we have a 2 sitting here, so we'll just do one of these at a time. The first one inside here would be 150 to the 1/4. Right, that's the first root. And then we would change this next one into, the cube root is a 1/3. Then we do it one more time. Keep making these parenthesis sets. The last one on the outside is a 1/2. Then you just multiply across the top and bottom. So this is 150 to the 1 times 1 times 1, 1. 4 times 3 is 12, times 2 is 24. So that's using rational exponents. And by the way, you could keep going and rewrite this with just one root, make this the 24th root of 150 as well. So these would be the same thing as well. Same thing back here. You could write this as the 8th root of 6. It's kind of like you're piling up all these 2's together. 2 times 2 times 2 gives you the 8. It's all the same thing. But what I have boxed in is what it wants, rational exponents. But they are the same thing. Because that's everything. And then you're going to try the huddle. There's an example where you do geometric mean. Write this in 2 different ways. That doesn't seem too difficult. Evaluate some of these without a calculator. Going back to the table, if you remember how to do that, and use the table. This one you need a calculator for. It's probably going to be a decimal, I guess. Write it as a single power using a rational exponent and then simplify. Okay, we did some of those. That's not too bad. Here you're going to have a bunch of 1, 2, 3. There's 4 of those. I might want to do number 7. This one you want to keep as a radical symbol, so you want to keep the radical in it. 10 seems tough too. Might go over those ones. So let's finish up with these couple in the huddle, and then we'll be done. Number 7. Whoops. So if you look at this one, I'm going to do something a little different here because I looked at this and I noticed that this is a square root of 81. So I can actually do the square root of 81. What's going on here? Give me a pen. So instead of actually combining all these root symbols, I'm actually going to do the square root of 81 to take care of one of these. And the square root of 81 is 9. And so that takes care of the first square root. How many more do we have? How many more do we have? 1, 2, 3. So now we have the square root, square root, square root. See, I took care of one by doing the square root of 81 and got 9. Right? Hopefully that makes sense. Square root of 81 is 9. So there's 3 left, but guess what? I can do square root again. The square root of 9 is actually, just using the one root, is 3. So that takes care of that square root symbol. So now I only have 2. Unfortunately, I can't square root anymore, so I'm going to go ahead and change these to one single radical sign. Since these are both square roots with 2's on them, that'd be like multiplying them together. You could say this is the 4th root of 3. You could also write this as 3 to the 1/2 to the 1/2, which is 3 to the 1/4, if you multiply those two together, which is also the same thing as this. So they wanted this as a radical sign, and so I'd keep it like that. Let me look at number 8 here. In 8, 9, which of the following expressions is not equivalent to the other two? So you're just going to simplify each one of these. I don't think that one's too bad. This would be 6 to the, what's 12 over 36? Is that 1/3? Yeah. This would be 6 to the 2/12, which would be 6 to the 1/6. Divide them both by 2. Well, these two are not matching, so which one matches this? Ooh. 36 to the 1/12. What is that? That's a tough one. That one I probably would not expect you to get. You probably have to type that one in the calculator. Because the only way to do this one is to break the 1/12 apart into 36. Because the 36 is a perfect square root. So if I had 36 to the 1/2, that would actually simplify down to 6. And then I would have to put a 1/6 here, right? Because 1 times 1 is 1, 2 times 6 is 12. So that would match. And then this would give you 6 to the 1/6. Which is not going to there too. It's this one. Those ones are a little tricky. How about this one? This one you can't do anything with it. You could put it back into this symbol, but I might just make them all rational. Let's see. Ooh. Here you have the 4th root of p squared with a 6 on the outside. So how do you do that? Well, these would both be in the numerator. So you could essentially multiply them together. This would be the 4th root of p to the 2 times 6 is 12. And then this would get rewritten as p to the 12 over 4, which is p to the 3rd. This one we have the square roots. So this would be like combining those two and saying the 4th root of p to the 6th, which would be p to the 6 over 4. And you could reduce that down to p to the 3 over 2, I believe. And so these two match. So this is the one that's not. Okay. So I did some of those with you. The last one, which would be probably the hardest one, is this one here. You have the square root of k to the 1/2. So this would be k to the 1/2. Square root means you got another 1/2. Whoops, put 1/4 by accident. The bottom, you have 2 square roots. You put them together. So you'd have the 4th root of k, which is, okay. Here you have k to the 1/2 times 1/2, which would be k to the 1/4, going across the top and bottom. And the bottom, change that to also k to the 1/4. Interesting. So these are actually the exact same thing. Okay. So you would have k to the 1/4 over k to the 1/4. They would actually cross each other out, and you get to the answer of 1. You can go ahead and try the other one as well. I don't think this one's going to simplify as nicely, but hopefully you get the idea of how to simplify these square roots and cube roots and going back and forth between a rational exponent and then a radical symbol. And that's going to wrap up 8.4. We'll definitely get into some harder ones in a little bit, doing more than just rewriting them in different forms. But that is the end of 8.4.